In this video, we will look at spatial diversity. What is diversity? And we will see different scenarios when the transmitter has multiple antennas and there are multiple antennas at the receiver. We will look at SIMO case where the diversity is applied at the receiver. We will look at MISO case where the diversity is applied at the transmitter, and then we will see MIMO case where the diversity is applied both at the transmitter and the receiver. So when we talk about diversity at transmitter, we generally consider two scenarios. In the scenario 1, when there is a feedback, and second, when there is no feedback. So feedback means the receiver sends a feedback to the transmitter sending the channel information. That means in this case, the transmitter will know about the channel information H. Whereas in case of no feedback, there will be no feedback and the transmitter will send a signal without waiting for the receiver to send a feedback. Thereafter, we will look at what is the diversity gain that is achieved. But first, what is diversity? So when we send a signal over the air, our aim is to receive a multiple copies of the same signal at the receiver so that we can effectively utilize these multiple copies to improve the gain of the system. And this diversity can be achieved in time, frequency, and space. So in time, we can send a same signal at different time, let's say signal at time t1 and signal at time t2 to achieve multiple copies at the receiver. In frequency, we can send a signal at different frequencies to have multiple copies at the receiver. But in both these cases, we are using extra time and extra frequency. That means we are using extra resources to provide the diversity at the receiver. Of course, there are certain ways by which we can achieve diversity in time and frequency, but we are not interested in that. Our motivation is to study how to achieve diversity in case of space dimension. So in space dimension, what we mean by this is, let's say we have a transmitter and we have a receiver. This single antenna at the transmitter and single antenna at the receiver. And this is the time axis and this is the gain that we achieved with time. Let's say these are the signal strength fluctuations over the time. And we know there is a level crossing rate and the average fade duration when the signal is below the threshold, and this threshold is referred to as gamma th. So now the moment when I add, but first the straightforward case to increase the receiver diversity or the way to reduce the probability of outage, that means these outage where the signal is in outage. The straightforward case is to directly increase the transmit power. So when I increase the transmit power, there is a shift in the signal, in the same signal, but there is certain shift. So this is the case as if we have provided a margin here and the signal hardly goes below the threshold value. So this is the margin here. But here we are using extra power to reduce the outage probability. The other case is to put another antenna at the receiver. So when I put another antenna at the receiver, this is the same receiver. And the antennas should be placed such that the signal received at this antenna, let's say Y1, and the signal received at antenna Y2, they must be uncorrelated. And to achieve this uncorrelation, this distance D should be greater than coherence distance DC. And when the signal is coming from all the directions, we have also seen that P of theta is 1 by 2 pi, and the correlation J naught 2 pi lambda x upon delta x upon lambda is equal to 0. From here we can get delta x is approximately equal to lambda by 2. So when we have this separation between the two antennas greater than lambda by 2, we say that the signal received at Y1 and the signal received at Y2, they are uncorrelated. And moreover, we will also use this narrowband assumption at the antennas, which states that the same signal is received at both the antennas, but they are shifted in phase. So now, when I put another antenna at the receiver, I will receive another signal. Let us remove this part. I will receive another signal. Let's say this is now the signal. And the idea of diversity is to select the signal that is higher, or only select the signal from the antenna that has higher gain. And from here it can be seen that it is the signal, the combined signal or the selected signal from the two antenna, it hardly goes below the threshold. And this is how, while adding multiple antennas at the receiver, we can improve the outage probability, or we can reduce the probability that the signal is going in the outage. And the advantage of this receiver diversity when we have multiple antenna at the receiver is that we are not utilizing more transmit power. In this case, the power is same, and we are not utilizing extra time and extra frequency resources. So there is no cost to the spectrum. But yes, there is a cost associated with this kind of diversity. That is, in case when we have multiple antennas, we have multiple receiver circuitry that will increase the power consumption of the receiver. And this is the intuition behind adding multiple antennas at the receiver, and how the diversity can be achieved when we have multiple antennas at the receiver. And this can also be understood by, let's say, if we have a transmitter and the signal is reaching the receiver, and we have a receiver here with single antenna. When I add multiple antenna, the surface area of the antenna will increase, and now with multiple antennas, the more energy can be captured by this receiver. And then when more energy is captured, the next step is to combine these signal in such a fashion that we will improve the gain of the system.